I'm Ruthu, and today I'll be presenting work I did with Dr. Debayan Gupta and T.S. Harikrishnan on how to create and remember more secure passwords by using methods optimized for us as humans. So we all experience something like this when we're making a password. And when the average person has about 130 accounts, it gets pretty overwhelming to remember so many passwords. So it's not a surprise to find out that most people handle this by using or reusing passwords. About 65% of people do this. And what does that mean? Well, if we're all sitting in a room together, about 100 people, then each person next to us is reusing passwords if we aren't ourselves. And this means that it takes less time to hack our passwords than it takes to type them. We wanted to understand this behavior, so we surveyed the 400 most popular websites online. Here's a summary of their password advice. About half want at least 8 characters in your password, and almost all of them want numbers, and a little more than half of them want capitals and symbols too. Only about 54 out of 400 of them, though, provide advice on how to do this. So that's less than 14% of them, which is about the same size ratio as a human to an ant. And the advice they give, like misspelling words and using symbol substitutions, is pretty misleading, because there's a lot of dictionaries with common misspellings and substitutions. The standard for managing so many passwords is password managers right now, but there are a lot of reports that even the most popular ones have 0-day attacks, so attacks that they can't anticipate until the 0th day. And writing down passwords isn't just a problem for us as humans. Even password managers write down the passwords to their password managers in plain text. Sometimes. So clearly, storing passwords anywhere, even in password managers or sticky notes, means other people can read them and use them. But we also can't remember so many strong passwords. Why not? Well, because passwords are strong when they're unpredictable, which means they need to be random. But our brains aren't built to generate or store random data. As humans, we have an associative memory, so we associate things with images, sounds, colors, or something else we know. So it's much easier for us to remember passwords if we make associations and connect them to sounds, or images, or colors, or other things. But learning 130 new associations, which is the average number of accounts we have, is just a huge task. So why not associate our passwords with information we already have in our brains? So this is exactly what we tried to answer with our research. How can we use information and associations we already have in our brains to come up with random passwords? Now, first we need to define what a secure password is, because we need a clear definition of success to be able to optimize our functions towards it. Typically, passwords are measured using entropy, so that tells us how unpredictable or random they are. But a password with high entropy looks strong, whereas in real life, that means it's harder to remember, so we just write them down or reuse them, and they become less secure. That's why we came up with the metric of effective security. So that measures how strong a password is in real life. And there's a lot of space for future work here on how exactly we can measure this mathematically, because we don't yet know the threshold of cognitive load. So after what point do people just give up and start writing passwords down, or start ignoring these algorithms and using easier passwords? So going back to creating passwords using information we already have in our brains, our brain stores information as sensory associations or electrical impulses. So the task we have is to find a function that can take these associations and turn them into strings of random text that also has numbers and capitalization and symbols. So we create passwords by associating specific memories with each website and using these functions to turn those associations into random text. Now, these algorithms have a few requirements. They need to be public so that they can be shared and everyone can use them. They also need to retain effective security, so they have to work even when people don't have access to pen and paper, or when people come from different language and education backgrounds. So we call that graceful degradation. And these functions also need to be pre-image resistant. And what that means is that, let's say someone has found all of our passwords and accounts. So they know what it is for Amazon, they know what it is for Facebook. Even then, a computer, a polynomial time adversary, should not be able to guess and find patterns among our passwords to figure out the memories or the associations we used to come up with them. And even if someone figures out these patterns or the secret key we're using to generate passwords, they still shouldn't be able to predict what our next password will be for a given account. Now, each function also depends on the unique layout of our memories. So, like a fingerprint that's unique to us, and these are our sources of randomness. This uniqueness is what makes sure that someone can't predict our next password. So this is called unforgeability under random challenge attack. And of course, the functions need to be collision resistant. So that means that there's only one secret that can produce a specific password. Now, in cryptography and security, we have hash functions that take in a key and create random outputs. But the problem is that these algorithms have math that's so complex that we can't do it without the help of calculators and computers. And that's why we came up with human-computable hash functions. So these algorithms are based on 3 or 4 well-known ways that memory engages with reality. And these can be sound, music, stories, associations, spatial navigation. And using these, we present 4 human-computable hash functions. So they're designed to test which of these approaches create the most effectively secure passwords. The first algorithm, Memory Palace, it's based on navigating a familiar place in your mind. So it uses spatial and visual implicit memory, so stuff we already know in our brains. And based on the letters in the website, we navigate a place in our minds, and whenever we stop the navigation, whatever we face becomes a word. We take this word and we split it into groups of 2. We add every pair of these letters to create a new letter. And for each of these new letters, from our keyboard, we add characters that are diagonal to them. So this is an example of a source of randomness, because the angle of the diagonal or the character we choose is unique to each of us. And it can't be predicted by someone else. This string is now our random looking password. So we have an association to it, but it looks random to everyone else. Now, if someone sees just our password, they can't guess the word behind it, because each letter in our password can come from 13 or 14 different additions of letter pairs, and this tells us nothing about the order of these pairs. So if we count that in too, the probability of tracing the letters in our password back to the original word we thought of is less than 4%. The second function is based on associative memory, so it takes in a story and a symbol as inputs. And we make a unique symbol table by remembering our favorite story and moving cells in our symbol table based on what happens in the story. So each event in the story has a movement associated with it. And you only need to create this table once, and then you can store it publicly. Now you connect your story to your website with a word. So for example, I might connect the story Star Wars to Amazon with the word lightsaber. But the advantage here, the great thing is that even if the story and the website become public, it's very hard to guess the word that you thought of, because for me it might be lightsaber, but for you it might be Emperor Palpatine or Baby Yoda. So we take a connecting word and we treat each letter as a coordinate, and we map that coordinate to a cell in our symbol table. And the letters in those cells become our password. In terms of pre-image resistance, similar to the Memory Palace, each letter in our word maps back to a cell in the symbol table, and there's so many possibilities of letter coordinate mappings that even with a really powerful computer and a public symbol table, it's quite hard to find the secret or the memory we used. The next function uses songs and a 4-digit PIN, so it's designed around musical associations in memory. We choose a 4-digit PIN, we reduce the website name to 4 letters, and choose 4 songs starting from each of those letters. And then we take words from each song based on our PIN. So for 1, 2, 3, 4, it will be the first word from the first song, the second word from the second song, and so on. After each vowel, we add the closest character to it on the keyboard. And then we randomly choose 3 different letters and move them to the end of the string. And then we remove every alternate character, and that becomes our password. Now, moving and deleting characters means that the final password doesn't have any identifiable words, so it can't be attacked using dictionaries of words from different languages. And we also can't trace the password back to words in the song itself, or the 4-digit PIN, so it's very strongly pre-image resistant. We also can't predict which characters we removed because we shifted some characters around before we deleted them. And that prevents any letter frequency or position-based attacks. The last function uses implicit and associative memory without any constraints. So we ask people to take a rare word, maybe like supernova, and connect it to our website using a sentence like Amazon will buy supernovas. And that's our password. Now the pre-image resistance here is low, and that means it's also unforgeable under random challenge attack. So that means that, for example, here we can easily see after a few passwords that supernova is a repeating word, and so we can deduce that that was the secret that we used. And so with frequency analysis, we can easily find keys or secrets. Now, to evaluate these functions and measure how good they are, we surveyed 134 people between 18 and 25. They tried to create passwords using our algorithms, so they were assigned 2 random algorithms on their first day, and they came back within a week and tried to remember them. We also include an algorithm called Cuban Select in our survey. This is from the pioneering work of Blanchard et al. In Human-Computable passwords. Unfortunately, it was only tested on the sample size of 11 people originally, so we test this along with our own functions. The population for the survey was drawn from students in an Indian university, so they come from a range of different language, education, and income backgrounds. And the advantage here is that most of them are bilingual, so one language they know is in English because our survey is in English, and they know at least one other language, their mother tongue, which is completely unrelated to English or its Latin roots. And the advantage is that most password-related surveys are conducted for people with Latin-derived languages. So this gives us some new insights. The caveats of this population is that we don't know how these functions work for other ages, and the survey population also has selection bias, so we only have responses from people who signed up for the survey in exchange for cookies and money, and the data is also self-reported. So how do we measure how good an algorithm is? Well, we use a combination of how much randomness each algorithm introduces into passwords, whether these algorithms are UFRC secure and gracefully degrade, and also how easy they are and how easily their passwords can be remembered. So this research is very exploratory because unlike security, when we know that 72 or 80 bits of entropy is good enough for the next couple of years, we don't know exactly how much recall is enough. So is 80% enough? Is 50% enough? We don't know yet. And we also don't know the cognitive threshold. So how hard is too hard? How hard can we make something until people just start giving up? But we're using these metrics so that we can compare and rank these algorithms and understand what is enough. And we're also in the process of designing a new survey to answer some of these questions. So here are some of the passwords that were generated using our algorithms. These passwords have twice the normal entropy, so they're twice as random as usual. And it's the capitalization using these algorithms is also more distributed. So usually in passwords, the first letter is capitalized, but these algorithms encourage more distributed capitalization. The average length of passwords that these algorithms create is also good for many website and security standards. And Otherwise, the algorithms can always be modified to increase this length easily. These functions can be done in 5 or 10 minutes, and they get easier with time. So to test how well people could remember their passwords using just their secret or the key, their memory, they tried remembering them within a week. And for about 50% of people, they were able to recall the entire password perfectly using the algorithms of internal sentence and memory palace. And about 60 or 70% of people were able to recreate parts of their password using these algorithms. So here's another representation of recall. Here, bigger bubbles mean more people could remember more of their password perfectly, and smaller bubbles means less people remembered less of their passwords. The trend we can see here is that the methods that need more explicit memorization, so learning new information, have lower recall, whereas the combination of implicit and associative memory is what creates high recall. So if the cognitive load is low, basically recall is easier. That's why we also suggest using partial visual cues. So these are half-completed line drawings, and we can use these to reduce the load of even having to remember, for example, the objects that we saw in our memory palace navigation. I'll give you a second to see if you can recognize what this is. So the important thing here is that visual implicit memory-based tasks are accessible to neurodiverse people too. So people with neurological damage or differences can still succeed at these implicit memory tasks, even if they can't succeed at explicit memory tasks sometimes. So analyzing these functions in terms of collision resistance is tough, because to do that we need to generate millions or even billions of passwords, and since these functions use the unique configuration of our memories, it's impossible to artificially generate datasets like that. But our analysis suggests that the probability of a collision is about 2 power minus 78. So that's like trying to find a football, one specific football in a planet made of footballs. It's pretty hard. And the way collision attacks work is by trying out different secrets and seeing if the passwords produced using those secrets match our passwords. So we'd say that it's not even a question of how many tries that an adversary can make to find our secret using a collision. They can't even try once because they can't follow the same exact algorithm using the same exact way that we did it. We also tried using machine learning to predict the next character in these passwords. If we gave it all the previous characters of the password, so the more random the password, the harder it is to predict the next letter, essentially. Our survey results also gave us insight into the tasks that people find cognitively challenging, and in the future we can optimize towards changing some of these tasks. So to conclude this journey, we've seen that password security isn't just about having strong random passwords. It's about making connections between passwords and images, sounds, stories, something we already know, to be able to remember those passwords. We've come up with human-computable hash functions to create these associations and to reduce cognitive load so that we just have to remember one key or secret to create all of our passwords. And we don't need to remember any steps because these are all public. So they still protect our secrets, but they're public, and they use our unique memories to do this. In the future, when we're thinking about password security, we should remember to think about public algorithms, and we should remember to reduce the cognitive load of remembering steps and the tasks we have in our algorithms to try to optimize them to be easy for humans to do. Now, all of this is because at the end of the day, we all want our privacy to be respected, and we want to make sure that our personal lives and our work are protected. And for that, we need to start by making more secure passwords. So I'd like to conclude by thanking my co-author T.S. Harikrishnan and Dr. Debayan Gupta, without whose guidance this wouldn't have been possible, and also Ashoka University, and of course you, for listening with your attention and your time. Thank you so much.